Alright, silly people, here's the situation. Imagine, if you will, that you had a Lagrangian, L, let's say, and it obeys an equation of motion which you can derive from the Euler-Lagrange equation. Uh, what if we had a new Lagrangian, which was the same Lagrangian plus the total time derivative of some function f, which is a function of the 4 position and time. Let's actually expand the definition of the time derivative of f, actually, because via the chain rule, you're going to be doing a partial derivative of the function f with respect to alpha times the time derivative of the x alpha plus the derivative of the function with respect to uh, time, so the del f del tau. Um, and then we can even simplify this further because we know that the time derivative of x alpha is u alpha. So we have this sort of thing going on here. And I'm actually going to write it now as just del super alpha f, right? And then this is going to be del f del tau. Cool. Um, Now let's do Euler-Lagrange's equation on this. So first we need to take the derivative of it with respect to the 4 velocity u mu. So the only term in here which actually depends on u is the middle term. So we have a del u alpha del u mu times del alpha f, but then also presuming the Lagrangian L, you can take a derivative of that with respect to u mu. Okay, the derivative of that thing is actually just a Kronecker delta, so we have delta alpha mu, and this is going to be delta alpha f, and then this is the partial derivative of the Lagrangian with respect to u mu. We can let that Kronecker delta act on the spatial derivative of f. So we'll have del mu f plus del L del u mu. Okay. Now we need to take the total time derivative of this junk, which is going to be del mu df d tau plus d tau del L del u mu. And we can expand the definition of the time derivative of f again. So we're going to have u alpha del mu del alpha f, right? So that's what that's looking like, and that's very cool. Now we actually need to take the derivative of the Lagrangian with respect to just x mu. And then looking in here, the only things which depend on x mu are the Lagrangian L. I guess I should put primes here. So x mu there. And then also plus u alpha del mu del alpha f. Cool. Yeah, that stuff will depend on position. I don't think the function of time derivative of that would depend on position, so I think we're good. So putting it all together, we have that this thing plus d dt del L del u mu minus this thing, so del L del x mu plus u alpha del mu u del alpha, and this is actually a minus sign overall. All this is equal to 0, according to Euler-Lagrange equation. But this term cancels out this term, and we just get the same equation of motion back. So that's why these two Lagrangians are actually said to be equivalent, L prime versus L, because they produce the same equation of motion. So Jackson also wanted us to check this idea on a Lagrangian, which he found early in the chapter. This is going to be minus mc squared. We got 1 minus u squared over c squared under a square root plus e over c u dot a minus e phi. And I'm actually just going to work in natural units because I can. So I'm just going to let c go to 1 wherever it shows up. So we have something that is a little bit less silly. E u dot a minus e phi. And so Jackson asks us to do a Lorentz gauge on this. So we're going to let a alpha go to a alpha plus del alpha lambda, is what he said. And so we actually need to get like the time components and space components of this to match the notation of the Lagrangian. So let's do alpha 0, which is phi, goes to phi plus, and then this is the time derivative of lambda, a partial time derivative. That's important. It's a partial time derivative. And then we can let alpha be the space components, so this becomes the vector A. On the other side, this is the vector A, and then actually minus del, and it becomes, the gradient of lambda. Yeah, because when we sum over the spatial derivatives, we get minus gradient lambda. Okay, so just going through the Lagrangian and writing out what the new Lagrangian is, given the Lorentz gauge. This is going to be plus EU dot, and then this is going to be A minus gradient lambda, and then minus E times phi plus del lambda del t. Okay. We can simplify this a little bit. So we're going to get E u dot a. We recover that term from the original Lagrangian. We recover this term from the original Lagrangian, but then we also have this minus EU dot gradient lambda minus E partial derivative of lambda. If we collect those two terms into one little term, we have E, and then this is going to be the velocity, so dx d tau times gradient lambda, gradient lambda, minus, or plus actually, because there's a minus sign up front, del lambda del t, or tau even, it doesn't really matter, because this is just using the chain rule, a total time derivative of A, or of lambda. Yeah, the lambdas and the A's get a bit confusing, but yeah, it's a total time derivative of lambda, presuming lambda is a function of position and time. So we recover a Lagrangian that is the same as the Lagrangian from before, just with a time derivative of a function, which means effectively that the Lagrangians are the same. They'll produce the same equations of motion. But yeah, enjoy that.